218, that sounds good. Okay, it's 2 p.m., so I'm going to let a few more people trickle in, and then I'll get started. Okay, I'll go ahead and start. This is Introduction to Kernel Hardening. First, a little about me. I'm Laura Abbott. I'm a full-time employee on Fedora Engineering. I'm one of 3 kernel maintainers, the others being Justin Forbes and Jeremy Klein. On a day-to-day basis, I'm one of the people looking at Bugzilla, making kernel builds, and generally keeping kernel flowing. But apart from my official full-time duties, I spend some time on various side projects and other things in the kernel. And one of those I've taken interest in recently is security. I do consider my primary role to be a kernel developer, but again, the interest in security has let me learn a little bit more about other aspects of the kernel. So this is what I intend to cover during this time slot. I'm going to give a brief introduction to the general concept of security hardening, then discuss some of the non-technical reasons why in the Linux kernel this has sometimes been kind of controversial, and then finally I'll wrap it up by talking about some of the actual hardening features that have been merged into the Linux kernel recently. So security is a very broad topic. It can cover a wide variety of areas. Just look at DevConf under the security track, you'll see any number of things covered. But the primary focus of this talk is going to be security bugs security issues caused by code bugs. Code bugs are always going to happen. What differs from project to project is when those bugs are found and how they're responded to. Okay. So this is a classic example of buggy C code. For those who haven't seen this before, gets is a function that takes that reads from standard in and stores data in the buffer. But there's no bounds check on the amount of data that gets will return, and it will happily write past beyond the end of a buffer, causing corruption or any number of kinds of problems. So in this example, the array A is stack allocated, so what's going to get corrupted is the stack. And an example I'll give shortly, it turns out it's pretty easy to make the program do whatever you want when you can control the stack. And this is really the classic Stack Overflow vulnerability, which has been responsible for any number of bugs over the years. And a classic example is the Morris worm, which was a contributing factor to gets. So if gets is buggy, what exactly do you do about this? And the fact that gets has no bounds check means that there's really no way to use it safely. So the only solution is to remove it from your code, as this man page helpfully describes. And these days, gets has been gradually removed from everything to make things a little bit better. And so it's generally been deprecated. So one replacement for gets is fgets. Fgets can work slightly differently, but can also work on standard in and store stuff in the buffer, but this time it takes the buffer length. But the problem is that you still need to actually set the buffer length correctly. So in this example, we're giving fgets a bounds of 100, even though the buffer size is only 10, so you're still going to have a problem. And obviously this example is still incorrect, and it's pretty easy to see this, but it turns out it's pretty easy to introduce the same type of bug, say stick an extra 0 on the end of a bounds and have it being missed during code review, and so you still have a bug. And so the moral is you can get rid of particular functions that may be buggy, but you may not be able to ever get rid of, stop someone from re-implementing gets or doing gets-like behavior in a similar manner. Okay, so obviously, like I said, you're always going to need to fix the bugs, but this sort of gets to the bigger picture question about, okay, well, is everything actually futile? Can we do anything about this? And the answer turns out to be yes. And this is the goal of security hardening. For security hardening, you're always going to have bugs, but the goal is to hopefully limit what those bugs will actually be able to do to potentially damage your system. Okay, so I'm going to give a short demo. Okay, so this is the small buggy C program before with gets, and there's also another function below which also to do. So we can compile it. As you see, GCC is happily telling me you shouldn't be doing this, but we're going to do it anyways. So I'll give a few examples about how we can run it, say, with safe input and with unsafe input. And it's seg faults. And in this case, we're just giving it garbage to make it seg fault. But it turns out if you're clever about what input you give it, you can make the program do something more interesting, like, say, execute the other function. Full details about what this is are a little bit out of scope, but at a high level, this is putting data in the buffer, and then we're putting specific values after that we want to overwrite on the stack. So in this case, one of the values is a frame pointer, and then the other value is the address we want to jump to. So you can see we managed to print out the other function. So this talk is about hardening, and the answer is, okay, what exactly can we do about this besides just removing gets? And it turns out GCC has an option called fStack Protector. And what the stack protector does is it adds various checks at runtime to detect if you are overwriting the bounds of the stack. So the hope is that your program will instead just be killed or abort instead of actually doing something you don't want it to. So okay, in this case, you can see it was compiled with -f stack protector, and if we run it again, you can see it says stack smashing detected, and it aborted. So the stack protector is not perfect. It's not going to catch all cases, but it provides a good example of a baseline defense against some level of bugs that your program might cause. Okay, yeah, so that was a little demo, give an example of hardening. And it certainly makes things more secure, but part of the issue with hardening and other other features like this is that you end up having to make trade-offs in terms of performance and size. So in my small program example I gave, just adding fStack Protector increased the text size by 200 bytes, which doesn't sound like much, but if you think about the increase over a larger program or library, it really starts to add up. And likewise, the runtime's checks against to try and detect if the stack is corrupted also starts to add up over the lifetime of a larger program. And so this brings us to a bit of history. The Linux kernel has historically not been the most open to security and hardening features. The philosophy held for many years was just that the focus needed to be on features and performance, and most security-related work was that would degrade either of those was just not welcome because it was a trade-off kernel developers weren't willing to make. If you search LKML, you can find plenty of rants from Linus and other developers, talking about exactly what they think of the security developers. But of course, there were plenty of other people out there who were in fact interested in improving securities. And one of the most well-known projects for securing the kernel would be grsecurity. Grsecurity is an out-of-tree patch set that's been developed since about the 2.4 timeframe. It's certainly been around for a long time. And the grsecurity patch set implements a number of hardening features and will make your kernel possibly reduce the performance and get rid of a few features, but at the cost of increased securities, because that's the trade-offs the grsecurity developers wanted to make. And there's often a lot of discussion about, well, if grsecurity is so good, why isn't it just merged into the mainline kernel? And that's kind of, a loaded question. But the answer there is that to get the level of security the Gr developers actually wanted, they had to make fairly intrusive changes to the Linux kernel. And to get those accepted into mainline, they would have to adjust their changes to the satisfaction of upstream developers, and they have elected not to do so. This is not really a knock against the grsecurity developers, just because they are not the only developers who have decided they would rather maintain an out-of-tree patch set than deal with the upstream kernel community. And honestly, if Linus is insulting your work personally, there's not a lot of motivation to want to clean things up. Okay. So things were going along as normal for years. Grsecurity had more hardening features. The upstream Linux kernel was having bugs and fixing bugs. And eventually, people started to take a look and do some analysis, especially as some of these big named bugs came about. And they discovered that there was an average of 5 years between introduction of a security bug and the time it was actually fixed, which is a number of years when things were vulnerable. And then we have Android. Android phones are not particularly well known for getting timely kernel updates. Admittedly, this has been better over the years. But the fact of the matter is that if a bug is fixed upstream, it does your Android phone no good if you never actually get a kernel update with the fix. So people start to look at this and realize that if you're going to be running a system that could be vulnerable for a long time, what exactly can you do? So several years ago, Case Cook from Google realized the kernel was very far behind in the security area, so he started to organize developers under what he called the Kernel Self Protection Project. And this was really an effort designed to bring hardening features into the mainline Linux kernel. And a lot of the basis for the work was the grsecurity patches. And honestly, this has been kind of controversial at times, and the grsecurity developers have, not always been particularly happy, and it's taken a lot of back and forth to make sure the grsecurity developers got proper credit for their work, which they absolutely deserve. And I'd like to point out that, I'm talking about this back and forth and this conflict, not because I want to point fingers or fling mud, but because non-technical conflicts are just as blocking as technical conflicts. And if they're going to prevent features from going in, they need to be solved. And just ignoring them doesn't actually do anyone any good. Okay, so that's some of the background. Now here are some more details about what exactly has been done so far to secure the kernel in terms of hardening. And this has happened over a number of kernel versions. So one fairly basic area of hardening is to set the strictest kernel page table permissions possible. There's no reason, for example, the kernel text should ever be writable. It's set up once at boot and never changed. And another example is that the kernel heap should never be executable. You should really never be trying to execute anything except the text. So what you should really be doing is making sure the kernel text is non-writable and kernel heap is non-executable. And permissions like this had existed sort of piecemeal across the Linux kernel, sometimes being set up sometimes not being set up, sometimes being marked as a debug feature. So there's some work to really make sure everything had the minimum permissions possible. And this also was true for modules. Modules have their own mapping, so they need to have their own appropriate permissions set. And as part of this work, there's now checks to be able to identify possibly vulnerable pages as an identification that maybe something's been set up if you have a page that's both readable and executable. And the continuing thing of making sure everything has the most restrictive permissions possible, there's work to identify structures and other variables that can be made read-only, either that are never actually written to in the kernel or are only written to one string initialization and then never touched after that. Okay. So virtually mapped stacks are a feature that was introduced for x86 in the 4.9 kernel and ARM64 in 4.14. So kernel memory can be broken down into roughly two categories, directly mapped or virtually mapped. The majority of memory in the kernel is directly mapped. It's set up once at boot and never changed. And what you can typically do is take any direct map virtual address, do some simple arithmetic, and get the physical address. The flip side of this is that if you have a direct map kernel address and you do some simple math, you can typically get to any other virtual address as well. See also the example about KASAN and writing out of bounds. And kernel stacks used to be directly mapped allocated, which meant that if you overflowed your stack, you could happily write into anything else that was there, which might be your thread info, which contained, your permissions, or another thread stack. So virtually mapped stack was an attempt to make it so that the stacks were allocated virtually, which meant that if you overran the stack, you would simply take a page fault and the thread would be killed. Like I mentioned before, there are some trade-offs here in that virtually mapped stacks had some penalty in terms of performance, just because you do have to sit down and create and tear down the mapping at runtime. But overall, I think it's now a fairly standard feature. And another side effect of the virtually mapped stacks was there were a lot of places in the kernel where drivers were attempting to assume the stack itself was directly mapped. So there was a lot of cleanup to make sure drivers were not attempting to do things like DMA from the stack. And those have mostly been cleaned up these days, although you'll still find an occasionally obscure driver that's trying to do DMA from the stack. Okay. So there's a set of APIs for copying data back and forth between kernel and user space. The copy to user, copy from user APIs. And these are designed to be a sync point where to do permission checks to make sure that the kernel address is valid, the user address is valid, et cetera, et cetera. And these are true and there are checks. But it turns out there were still a lot of various ways that things could go wrong with these APIs. And grsecurity has had more stringent checks here for a while, so this was one of the features that was ported over from grsecurity. And now if you enable the harden use a copy feature, there are some kind of basic sanity checks about things that should never really happen, such as trying to copy kernel text to user space and validating a few bounds. If you've allocated an object of size 64 and you're trying to copy 128 bytes from that object to user space, something has gone wrong. So these checks aren't going to catch every bad use, but the goal is to provide a solid foundation of things that should never really happen. Okay. So I demonstrated the stack protector in the demo, and it turns out there are a lot of ways to harden the kernel if you can change the compiler. So GCC has support for a plugin framework for custom compiler passes. And then again, grsecurity has had support for plugins and a few hardening plugins for a while. So those are one of the things that's been ported over to the Linux kernel, as well as a couple of the plugins. So a semi-common vulnerability is an information leak of kernel data or addresses to user space. And one way this happens is from uninitialized variables. Thanks to C is that if you have an uninitialized variable and you try and copy it, there's a pretty good chance you could be copying kernel addresses to user space. So one of the plugins ported from grsecurity was a plugin to make sure that uninitialized variables that could potentially be copied to user space were always initialized. And there's ongoing work to port another plugin called the stack leak plugin, which makes sure that when you exit a system call, the stack gets cleared. So that way, if you had another exploit to try and say read the stack, you wouldn't be able to leak kernel data. You would just read the poison values. And yeah, so I'm going to speed up a little bit here and summarize this. But a side effect of a lot of all this is that as part of doing the hardening work, there's been more unit tests for each of these features to make sure things are always correct. And those are ongoing and is hopefully a good example to the rest of the kernel about how to do testing and make sure things are running. OK, so wrapping things up here, Linux has made some much needed progress in increasing security. But it's important to work that security will never be done. Individual features may be considered complete, but there will always be new attacks and new techniques to implement. So that's all I have to say. So I think we have a few minutes for questions. Yep.
So currently, if I want to harden my kernel, then the best thing I can do is to recompile it with the patch from the grsecurity.
I mean, it depends exactly what you're looking for. If you think that the grsecurity patches provide what you want, then you can run with it. But it's also an out-of-tree patch, and that means you're doing the work to maintain it yourself. That's a perfectly valid option for some people, but again, it depends on exactly what you want to do. The goal is really focused for Kernel Self Protection Project is to try and get more of the features upstream, so everyone can take advantage of that without having to do the out-of-tree patch set. That's kind of hedging your question, just because it's ultimately up to you if you think that grsecurity is the right option for your needs.
Why do Google think that providing systems like Android where the user cannot upgrade its kernel and then trying to introduce some specific logic to hook kernel in a fixed security box is better than providing a way how to upgrade the kernels more easily? But it seems something like that.
I mean, I think that the question is about Google providing kernel updates and options they have, and I think it kind of goes to, I agree with you that it would be nice to be able to get upgradable kernels, but I think as far as delivering an Android release, I can't speak to fully why Google decided to do this process, but I think a lot of it has to do with I've worked on Android phones before, and it's pretty hard to actually get stuff out and give updates, and there are a lot of reasons why they don't allow you to add your own kernel, although I agree being able to upgrade your own kernel would be very nice. So.
That's not the energy should be focused, right?
What should be focused?
The energy to have a system where you can upgrade the kernel instead of having a way upgrade some, I don't know, what was the name, the case spec or what?
I mean, KSPP is for the upstream kernel. The upstream kernel ultimately is what goes into Android, so having that be updated is going to be ultimately a longer term better. I mean, your question goes to what is Google doing? I can't really answer why Google decides to do what they want to do. So, I mean, that's certainly a part of the ecosystem in question. So, okay, I think we're out of time now, so thank you.